Welcome back to the next video, everybody. Today we're going to proceed further into chapter 8 by looking at descent of group representations. So the question of the day is, let rho from pi to gln of a be a group representation, and suppose that the associated character chi sub rho of x, which is the h race of rho of x in a, has the property that it takes values in a subring a naught. That is, all these traces live in some subring a naught of a. We might ask if there's a descent of rho to a naught, i.e. a continuous representation rho naught from pi to gln of a naught, such that when we extend scalars using the tensor product from a0 to a, rho is isomorphic to rho naught. Okay, in other words, rho is isomorphic to rho naught with after extension of scalars of rho naught. The answer is yes, if a is a coefficient ring, which is what we will be dealing with, but it's no in general. If you want general results of this type, you can see Mazur's original deformation theory paper. You can also see Gouvet's arithmetic of p-adic modular forms. The most general result, the positive result, is found in the Carriol and Sayre references from the previous video, but we're going to just look at that result here today. Okay, we're going to give a quick overview of it. Let's let R be a commutative local ring with maximal ideal M sub R and residue field K. We'll let R from the completed group ring R bracket pi to Mn of R be the R algebra homomorphism associated to a given continuous representation rho from pi to gln of R. See the previous video. Okay, and we're going to assume that R is surjective. Again, see the previous video for why. Let's let R naught be the local subring of R with maximal ideal Mr naught, which is Mr intersect R naught, and residue field K that actually lives in K. Let's suppose that all the traces over R of alpha for all elements alpha in the completed group ring R bracket pi actually lie in R naught. Okay, so all the traces live in some actual local subring R naught of R. The answer to the descent question on the previous slide is yes, if, for example, the image of the completed group ring R naught bracket pi is in MNR is actually isomorphic as R naught algebras to Mn of R naught. Of course, then it's definitely true. Now, this isn't always the case, even though you might think it should be, but it sort of almost is. Okay, so let's talk about what I mean by that. An Azumea algebra sigma over R is a finite flat R algebra, such that sigma mod MR sigma is a central simple K algebra. The rank of such an algebra over R is its rank as an R module, which is the size of a maximal R linearly independent set in sigma. Okay, so for example, Mn of R is an Azumea R algebra with rank n squared. It's like a trivial example. Okay, below is the fundamental result regarding these algebras that we want. So proposition 3, let's let R from R bracket pi to MNR be a surjective R algebra homomorphism, and let's let R not be a local subring of R as above, where R is additionally an A algebra, where A is a coefficient ring. Okay, suppose that all the R traces of all the R alphas lie in R naught for all alpha in R bracket pi. Then the image kind of cal R naught in MNR is an Azumea R naught algebra of rank n squared, such that the natural A algebra homomorphism take cal R naught and tensor it up to R over R naught, send that to MNR. That's actually an isomorphism of A algebras. Okay, so this image, if you just tensor it back up to R, so in other words, if you extend scalars, gives you an isomorphism onto all of MNR. Okay, so we do have kind of an affirmative answer in this case. So proof, you can see the Carriol and Sayre references I gave you last video. You can also see the Cornell-Silverman-Stevens book, page 255, for a sketch of this argument. All right, how do we use this? To use it, we need another theorem of Azumea, which says that the Brouwer group of a Henselian local ring, i.e. the group of central simple algebras over this ring, modulo some kind of natural special equivalence among these algebras. You can see Milne's class field theory for the definition and construction and basic properties of the Brouwer group. Okay. The Brouwer group of a Henselian local ring is isomorphic to its residue field. Okay, you can see Azumea on maximally central simple algebras, and also this other paper by, I'm not even going to try to pronounce these names. Okay, I can effectively use this result because my coefficient ring A that I'm working over under this generic setup of Galois representations, these are Henselian actually. This is because they're complete local. You can see Stack's project tag 03QD, for example. Okay, this means that because they're Henselian, they're going to have finite residue field. And so that means they're going to have trivial Brouwer group by basic properties of Brouwer groups. Okay, so what this means by definition then is that coefficient rings don't admit any non-trivial Azumea algebras. So what's the upshot? Corollary, Let rho from pi to GLN of A be absolutely irreducible. Remember, that's the same as the corresponding R being surjective from last video, so that we can use the above setup. And let A naught and A be a local subring of the coefficient ring A such that all of the A traces of rho of X lie in some A naught for all X in pi. Then there is a representation, rho naught from pi to GLN of A naught, which after extension of scalars from A naught to A is equivalent to rho. In other words, the answer is yes in the setup that we're going to be working with, which is Galois representations into GLN of coefficient rings, as long as we have absolute irreducibility. Okay. Note, however, as a closing remark, that the ring A naught in the corollary, however, may have a smaller residue field than that of A. That is, the injection from A naught to A may not actually be a coefficient ring homomorphism. It might just be a generic kind of homomorphism of rings or of algebras. Okay, so we'll see how to fix that much later, but that's the end of the video. So I'll keep pushing into chapter 8 next time. We'll sort of tie all this into Galois representations. So I'll see you all then, and thanks for watching.